This is section 7.2. We're going to start talking about the Laplace transform. So if f is a function on 0 to infinity, so as long as it exists from 0 to infinity, including 0, that's what that square bracket means, then the Laplace transform of f is the function capital F that is defined by this integral. You take the integral from 0 to infinity of our function f times e to the negative st. The Laplace transform of f is denoted by either capital F or this cursive L of little f. Laplace transforms do not exist for every function. The Laplace transform exists only if the original function is both piecewise continuous and of exponential order. And we'll go over those definitions. A function y equals f of t is piecewise continuous over an interval a to b. So we'll start drawing here. We've got an a and a b, and we're looking at the function from a to b. If for every t value at which f of t is not continuous, the left and right side limits exist. So if we have a point where it's not continuous between a and b, such as this point right here, but the left side limit exists and the right side limit exists, then we're good. We're still piecewise continuous. An example where we would not be piecewise continuous from a to b is something like this. Just imagine that's perfectly vertical, where you have that on the left side, it's shooting off to infinity, and on the right side, it's shooting off to negative infinity. So neither of those limits exist. So we would say that that's not piecewise continuous between a and b. A function is of exponential order alpha if there exist positive constants t and m such that the absolute value of f of t is less than m times e to the alpha t. So this is talking about how quickly the function grows. So as long as it grows as fast, but no faster than e to the power of t, an exponential function. But if it moves any faster than that, if its growth rate is any faster than that, we say that it is not of exponential order alpha. The textbook provides good examples of f of t equals 1 over t and f of t equals e to the t squared as functions that do not have Laplace transforms. The function f of t equals 1 over t is not piecewise continuous due to the point t equals 0. We see when t is equal to 0, you can kind of draw this asymptote in here, and the left and right side limits don't exist. Whereas for e to the t squared, it is clearly growing more quickly. E to the t squared would grow more quickly than what do we have here? E to the alpha t. Because this exponent grows faster than this product. So that's what we mean when we say something that grows too quickly. So those are the ways we would fail in finding a Laplace transform, but those are the only two ways. If everything else is satisfactory, then we can move on. Here is just our little proof that e to the t squared doesn't work here, because you can actually just divide both sides by e to the alpha t. And you get e to the t squared minus alpha t, but as t approaches infinity, that's clearly not less than just some constant m. So the growth rate is too high. Okay, let's start. Determine the Laplace transform for f of t equals t for t greater than or equal to 0. So we plug in t as our function into our Laplace transform equation. And now this integral is going to require integration by parts. So we're going to let u equal t and then take that derivative to just be 1. And then dv is equal to e to the negative st, and we get that integral. Now remember uv minus integral v du. So this infinity, we have to be very proper about this. You can't actually just go around plugging infinity into equations. So we now have to change this form to be the limit as n approaches infinity. And then we're going to start plugging n in for our equations. So this is our u times v right here. And this is our v du. Now, the integral of negative e to the negative st over s, well, that's just positive e to the negative st over s squared. That's what we see right here. And then we plug in our n and our 0, because this is a definite integral. So we have n minus what you get when you put in 0. And this minus sign is actually going to flip these. So this becomes minus n plus what happens when you plug in 0. Now these zeros cancel out fairly nicely. This whole thing's getting multiplied by 0, so it just disappears. E to the power of negative s times n, we'll just look to the side for a second. E to the negative sn is equal to 1 over e to the sn. So as n approaches infinity, that clearly goes to 0 because the denominator is shooting off to infinity. So this is also equal to 0. What we have here is e to the 0 over s squared. So that's just 1 over s squared. But now all that remains to calculate is what is this limit? What is the limit of negative n e to the negative sn over s? Well, again, e to the negative sn means we can move that to the denominator. So that's equal to negative n over se to the sn. And clearly this is just a growth rates problem where this is growing linearly, but this is growing exponentially. So the denominator is growing much more quickly, so it goes to 0. So 3 of these terms all went to 0, and all that was left was 1 over s squared. And now you see this is true for s greater than 0. If s is less than 0, then this value diverges, clearly, because you'd be dividing by something very tiny. So this is our solution. The Laplace transform of the function f equals t is 1 over s squared. Now we have a property of these Laplace transforms called linearity. Let f, f1, and f2 be functions whose Laplace transforms exist for s greater than alpha. And let c be a constant. Then for s greater than alpha, the following two things hold. We have the Laplace of f of 1 plus f of 2 is just the sum of the Laplaces. And we have that you can take out constants. So now let's do another example. Determine the Laplace transform for f of t is equal to 8t plus 4. We're going to use our concept of linearity, so we can bust this up into a sum of two Laplace transforms, and we can take this 8 out as a factor. So it's 8 times the Laplace transform of t. Well, we just solved that the Laplace transform of t is 1 over s squared, so this becomes 8 over s squared, plus 4 times the Laplace transform of 1. Well, we haven't solved for that yet, so we need to figure out what the Laplace transform of 1 is. So this is just the integral from 0 to n of 1 times e to the negative st. We don't need to do any integration by parts or anything fancy here. We know that integral is just negative e to the negative st divided by s. Don't forget your little chain rule there calls for you to divide by s. Now, what is this value equal to? Well, e to the negative sn, we've been over this, that's just equal to 0. 1 over e to the sn as n approaches infinity. You're dividing by infinity, essentially, so it's 0. Minus e to the 0 is just 1. So we get negative 1 over s times negative 1 gives you positive 1 over s. So we reach that the Laplace of 8t plus 4 is 8 over s squared. as we showed here, plus 4 times 1 over s. So that's 4 over s. And then if you wanted to simplify, get a common denominator and such.